we go. So again, sort of starting afresh with this idea. Here's what I just want you to know. From this slide, instead of proving it to you, I just want you to be able to look at infinite series that are in this form. And there are three possible outcomes. Two of which we sort of looked at yesterday. And that is, if p is equal to 1, the series 1 over n to the pth diverges. That was the first slide that we looked at yesterday. What is the series? Does the series 1 over n converge? Also, we looked at what happens, that one, not 2. What happens when p is greater than 1? When it's greater than 1, it converges. We did an example of that kind of problem. It was, does the series 1 over n squared converge? And the answer is yes, it does. We have one more thing that can happen, and that is p could be less than 1. And when we have that, we have another series that diverges. This series, 1 over n to the p, are referred to as the p series. And by inspection, relatively quickly, you can classify them as convergent or divergent series. I might go ahead and just rattle off a few. Hey, you're walking down a dark alley and you see 1 over n cubed. Is that series convergent or divergent? Convergent. Convergent. Again, by inspection, just by looking at that number. Hey, different day, different dark alley. There's the series 1 over root n. Divergent. Okay, in this case, what is the p-value? 1/2. And 1/2 is less than 1. So you're judging everything having to do with the exponent on n and judging it against 1. You okay with that idea? Great, because I'm going to build on that idea. This series should starting to feel very intuitive to you. Convergent. Okay, now I'm going to start playing games. Convergent? Why? It's almost like 1 over n to the 4th, a known convergent series. This is similar to, and that's enough for you to declare it to be convergent. And you know what? For a quick reaction, get the answer right thing, yes it is. That is really enough for you to say that's convergent.
How is it almost 1 to 1?
Well, remember, we talk about this starting at 1 and going to infinity. When n gets really big, this plus 1 doesn't matter much. When I wipe it out, what does it look like? It looks like n over n to the 5th. Which you could reduce 1 over, or n over n to the 5th. What do you get? 1 over n to the 4th. Okay? And where the heck's that n coming from? Divergent. Why? Why?
It's similar to 1 over n.
Because it feels a lot like 1 over n, a known divergent series. By the way, I forgot to give you the special name for that particular series. The series
Harmonic.
1 plus 1/2 plus 1/3. Did I tell you what it was called?
Yeah, you told us it was the harmonic one a while ago.
Okay. Just want to remind you that's called the harmonic series. And the harmonic series diverges. Okay, so we've got a quick way of judging a lot of these series. All right? And we need that intuition. Not because this is particularly rigorous mathematics. It's not. But in the multiple choice section of the AP exam, a lot of it is that look at it and classify it. And do you need a lot of rigor to get a multiple choice question like that right? No, you don't. Look at it, you judge it, you move on. All right. 27 plus 15, 42. Remember, it's in two different pieces. The calculated part and the not calculated part.
Well, that seems awful.
Not right now, but yes, I will. All right. So, you now feel like you have the ability to judge these things? Let me build on this a little bit more. If I write that, 1 over n squared, pretend I wrote a sigma in front of it. Convergent? Okay. 1 over n? Divergent? There's the line between the convergent series and the divergent series. On the left-hand side will be the divergent series. On the left-hand side will be the convergent series. You might imagine... Did I just say that wrong?
Yes.
Well, the problem is, whenever I say the right hand, I have to imagine that this hand's going to the right hand. You don't know what it's like until you're standing in front of a mirror and you have to do that. Okay, so things like n cubed. N cubed gets bigger faster than n squared. It's also convergent. You know what else is convergent? 1 over a to the n, where n is bigger than 1. That gets big fast. No, it gets bigger even faster. One over n factorial. It gets big really fast. No, it gets bigger even faster than that. N to the nth. Okay, why do I do this? Because if we can think about how these things get bigger faster, we can lump them all together into things that would look like convergent series. You know what gets bigger even slower than n? 1 over natural log of n. That's going to be another one of those divergent series, if I make a series out of that particular fraction. And 1 over n natural log n, it's a little bit bigger than 1 over n, but it's still on the divergent side of the line. I could show that one's divergent by using the integral test. Yes?
Going back to what we learned before, would we be able to compare the rates of these? Or
Anything that grows at the same rate as like a sub n ends up having the same sort of convergent behavior as a sub n. So that time that we spent saying, which one grows faster? Or do they grow at the same speed? Those grow at the same speed problems all play into the intuition that you will use to do these kinds of problems. Now, I tell you all this about building up your intuition because, one, again, it's helpful in the multiple choice question. But two, I need you to have those intuitive skills in order to apply this thing called the limit comparison test. Now, I'm going to make your life really easy right now. Because we're short on time, ignore 2 and 3 for right now. Just focus on rule number 1. Here's what rule number 1 says. First of all, you are given a limit problem that you need to solve. Let's call it A sub n. This is your problem. The one that you see in the book. But there's this other mention of this other series that's based on B sub n. That's what you get to choose. Now, I'm going to tell you again, in these particular problems, you use your intuition to know, 1, whether the series converges or diverges. But 2, you use your intuition to determine what B sub n is. That it's like this other series. I'm not asking you, does this converge or diverge? I'm asking you a harder question with this. I'm asking, prove that it converges or diverges. Do you hear the difference between those two things? Look at the problem that's down at the bottom of the page. By inspection, can you tell me whether that converges or diverges? By inspection? Jordan, do you have an opinion?
It's going to converge.
Okay, Jordan says it's going to converge. Why? Why do you say that?
Oh, no, I'm sorry, I was saying that. Because you're going to end up with basically n over n squared, and that's going to diverge.
Did you hear that? On the top, it's basically an order 1. Order 1 polynomial. On the bottom, it's basically a order 2 polynomial. When everything's said and done, it turns into 1 over n. So here's what we do. Here's how we use the limit comparison test. We say, hey, I know of this series. And this series is 1 over n. And I know that 1 over n diverges. We've already proved that. Now we say, okay, the limit comparison test says if I take the limit of the series that I'm trying to prove is convergent or divergent, if I take the limit as n approaches infinity, it's the longest approaches arrow I have ever made. Know why? And I take the a sub n term and I divide it by the b sub n term. And who chose that one? You chose that one. I divide it by 1 over n. Oh, that's ugly. Let me clean that up. The limit as n approaches infinity of 2n plus 1 quantity times n over n plus 1 squared. Took this divide by a fraction, change it to a multiply by its reciprocal.
You're going to have order 2 on top.
I'm going to have an order 2 on top. I'm going to have the limit as 2n squared plus n on top. On the bottom, I'm going to have n squared plus 2n plus 1 as n approaches infinity. And what do we get when we apply the limit? Oh, don't make it so hard, Edmund.
Oh, 1.
No.
2.
2. Again, yes, I could apply L'Hopital's rule to that. But we could just say, hey, other things go away. I get 2n squared over n squared. This goes to 2. Now, take a look at what the limit comparison test says you can do with that. If I take this limit and if I get a value c that is positive but not infinite, positive but not infinite, either both A and B converge or A and B diverge. Whatever it is, it's going to be the same. Well, I chose one that was divergent. I got a limit that was positive and finite. My conclusion then, this thing must diverge as well. Now, we already knew it diverged. Jordan, you explained it very well. And that was a great explanation on a very intuitive level. This is the rule that allows you to say what you did was correct. Do you need to use this rule all the time? Only if they ask you to prove it. Do you hear the context of the two questions? If I ask you this question, you go ahead and you just say diverge. If I say, prove to me that it diverges, now we got to do all this other work. I hate to say this, it's like saying, what's 2 plus 2? Someone says 4. The right answer. You go, prove it. Oh, that's a whole different question.
I was thinking that in my head with drawing lines.
Sorry. All right. So here we go. We're going to do each of these questions in succession, and we're going to do them 2 ways. First, give me the intuitive answer. 2, take me through the proof.
Converges.
It converges.
Converges. Very good. Let's let everyone get caught up with it. Look at that and say, get rid of the crap. Get rid of the stuff that doesn't matter when n gets really big. And what do you get? 1 over a to the n and a bigger than 1. Can everyone intuit, I hope, that that's a convergent series? So if you see it in the multiple choice section, you go convergent, you move on to the next problem.
About 4 questions like this, maybe.
There's probably going to be 4 infinite series multiple choice questions total. The ones that are just tell me converge or diverge, those ones are almost always those Roman numeral 1, 2, 3 questions, where they give you 3 infinite series. Which ones converge? Is it 1 and 2? Is it 1 and 3? Is it 2 and 3? 1, 2, or 3? Yeah, so they almost always put them in the Roman numeral. Don't let that throw you though. Okay, now, second part of the question. Now we're in the free response section. Can you prove that this series converges?
Yes, we can.
Yes, because we say this thing looks like 1 over 2n. You say that's convergent. Why do you say that's convergent? I say it's convergent because it is a geometric series with r equal 1/2. Would you agree? You'd be wise to agree because I really know what I'm talking about here. Yes, Jordan.
Like AP, would you have to justify why the function that you chose,
Yeah.
why the series that you chose is?
You have to justify why you say it diverges or converges. But typically what ends up happening is that you either claim that it's a p-series, like we did in the very first example, or you claim it's a geometric series like we're doing in this example. Right?
And that value of, the absolute value of that r is less than 1 or
Right.
in between any one of them.
Like you would say, and the absolute value of 1/2 is less than 1. But typically, just saying, and it's a geometric series with r equal 1/2 is sufficient evidence to say that that series converges. So there's part 1. What's part 2 of this limit comparison test? Well, let's do the limit part. The limit as n approaches infinity of 1 over 2n minus 1 over 1 over 2n. We don't like that fraction within a fraction form. So let's rewrite it using the divide by the fraction means multiply by the reciprocal. The limit as n approaches infinity of 1 over 2n minus 1 multiplied by 2n over 1. And that limit Edmund is right. It's 1. Because as n gets really big, we don't really think that negative 1 is going to matter much, right? We essentially have 2n over 2n. Sorry. 2 to the n over 2 to the n. All right. Okay, so we've got a limit which is finite and positive. One of the series was a known convergent series. Our conclusion is, therefore, this is convergent as well. And typically you would throw in by the limit comparison test. You'd say the name of the test that you apply.
Can we abbreviate it as LCD?
Sure. I'm pretty sure, yeah, that should be acceptable. LCT, it's kind of like MVT, the mean value theorem, or the FTC, the fundamental theorem of calculus. Those are known acronyms in this discipline. Yeah, just make something up. By the TDF. That's the Todd Darren Fedor theorem. And TGIF. Which means, boy, I really wish this test gets overseen.
2 weeks. From
All right.
this very day.
Okay, you guys, your turn. Go. Pairs.
Okay, so this
I got this.
is essentially
I just said
the same
yeah, it says combining.
as
Are you ready with calculus?
Yeah, this is kind of
much we can say. Now the one we want
No, I
to
said Kelly. Those say Kelly and are you
is
ready?
that this is pretty much the same as 1 over n squared,
Okay, that's the microphone's big enough.
right?
Oh, n equals 2? Does that change stuff?
Because essentially it's the same because the n. This is a 1
What about
over
this
n.
other separator? If you're on a
Well, that
solid,
doesn't
that
matter
two,
because
then
we're just looking at
I'm thinking.
we're looking at the biggest one here and the biggest one here. So those
You use a feature, you have to like explain why.
That hasn't added before.
Well, your comparison series is what? Going to be what? 1 over n squared? And you would say
So it
convergent
converges,
because of the
yeah.
p series with p greater than 2.
Okay.
Sorry, p greater than 1.
So
P
my
series is a known name, a known way of looking at
and that means
at
1
series.
over n squared
the limit
is
that approaches
a
infinity
p
up
series
3n plus 2 over n
a p value
times
greater than 1. Therefore, it is convergent. Then we go here
when n
to the
squared
limit
cancels that 1n
as n approaches infinity.
plus 2
3n plus 2 over n cubed minus 2n divided by n squared
Okay.
over n squared.
So we start with some comment like sigma of 1 over n squared is a known convergent series. It's a p series with p greater than 1.
I screwed that up or something. Okay.
Oh, yeah. Oh, yeah.
Essentially, this equals 3. Therefore, by the LCT,
It's 3n plus 2. That doesn't matter.
Well, it won't end up mattering, but it should be, I should put the same problem down there.
This is what we got. This is what we got.
why do people call this the hardest chapter?
Are you taking other ones though?
Okay. So we get to this point, and now we summarize. We plot. This limit is finite and positive. And the series 1 over n squared is a known convergent series Therefore, this series is also convergent because they're either going to both be convergent or both divergent. Okay, and I'm recording this, so you guys,
Yeah.
there's going to be lots of really good stuff after this.
Okay.
Really.
Fun stuff.
All right. Okay, and therefore this is convergent by LCT. Not to be confused with LCP. Oh, little sister, please.
Oh. Only on the first day.
We good with that?
Do you have to write that?
It would be really good to say that. Yes, I would say yes, you must write that. Okay, you ready? Another one. Go. And again, I want initial reaction. What's your intuition say about that series?
I think it's Okay, wait. So 2 to the 3 to the n. It's like 2/3 to the n. So that's like, which one of these is it?
Yeah. Wait. No, it's not.
What do you want to compare it to?
Two.
What does your intuition say?
2/3 to the n.
2/3 of the n.
But I don't know what that is.
And then you say that's a known geometric series. This is geo with r equal 2/3, and therefore it is convergent. So at this point right now, we're already into it that this other series is also going to be convergent. Now we just have to prove it. Oh yeah, prove it. I will.
I love
So that's why we used to talk in 5th grade. My dad's the strongest dad. Oh yeah? Prove it. My dad can climb up the rope in the gym without using his legs. Yeah, my dad could do it with no legs, with no arms. Actually, that's a true story. My dad could climb up the rope without using his legs at all. But my dad weighed about 115 pounds and worked for sheet metal, so it was like he had no body weight, and he had very small guy, but he could do amazing things. All right, continuing on. 2n over 3n plus 1 divided by the way, if you notice, there's a trick that you can actually skip to the second step,
Yes.
and then you just multiply this by the reciprocal. By the way, it makes it a lot easier if when you write that reciprocal, that you write, instead of 2/3 quantity n power, if you say 2 to the n over 3 to the n, which when you write the reciprocal, 3 to the n over 2 to the n. 2's cancel. And so what do we know about 3 to the n over 3n plus 3 to the n plus 1? Equals 1. 1 is a finite positive value.
between 0 and infinity.
Therefore, it's got to be convergent, just like the comparison series. So you can understand why it's called the limit comparison test. We have another function, another series which we compare, and we have to take the limit of it. Of course, if you choose the wrong series, you're not going to get a finite number. If you choose a different kind of series to do a comparison to, one of two things are going to happen. That limit's going to go to 0 or to infinity. Only if you use good intuition and choose a good comparison series does this work. Choose poorly, you'll get a 0 or an infinity, and it's inconclusive. All right? And again, Ignore 2 and 3 for right now. Again, ignore 2 and 3 unless you become a math major. All right. No, that's not. Well, write it down now. That was not what I expected the next slide to be. Well, there's a couple ones where I looked at them and I'm like, that's a lot of work. How much benefit? No. Throw them out. So when I was doing the homework, I said, that's just not what you're going to do. Did we do this one? But we did that one. Okay, last one for the limit comparison test. With your partners, please. Do it quickly, please. Or we're not. Oh no, we're not going to. But maybe we'll get a good stop. We're not going to. We're not going to finish this. We're on 12 of 24. We're not going to finish this lecture today.
Oh, that homework was just randomly.
No, I accidentally went to that slide.
Got it.
N
Looks like we're going to finish
N
this.
over N cubed plus
Good
N.
stuff.
Okay.
Okay, so this is like
We
saying
can
it's
declare that this is convergent.
My
What does it look like? It looks like 1
expectation
over
would
N
be
squared.
Because that is
This is a P series.
So that's like infinity plus infinity.
Therefore, it is convergent.
I'm not.
Now we take a P series is
Oh, maybe it was 1 over n squared plus 1.
I guess where you have just a variable. You have one variable and then you have another variable. It's basically, I guess that's
Wait, hold on. One is
I
N.
don't know what the difference between that and the power series is.
And I know where n squared plus.
Mr. Fedor, what would be the difference between a P series?
Okay, I'm going to think about that for a bit. Okay.
What? Is P series short for power series? Yeah.
No. It's just for saying. It just means that we have a we consistently use P for that particular exponent. I don't know why. At least it's consistent with 2 textbooks. That's as best I can say. Okay. Comparison series, please. 1 over n squared. What did your intuition say? Converge. Limit as n approaches infinity of n over n cubed plus n multiplied by n squared over 1. Did you do that? Sure you did.
Of course.
Limit as n approaches infinity of n cubed over n cubed plus n is equal to 1. 1 is finite and positive.
Convergent.
Therefore, convergent
Because.
by limit comparison test. Great. Good. Now for something you're really gonna like.
Wait, like as in really like? Or
Like really like.
Okay, not like. So
Like I'm not yanking your chain here. All right? The alternating series test. In fact, I'm going to do what I do every year on this particular topic. I heart alternating series. Please let me explain. An alternating series is a series in which the sign will go back and forth from plus to minus, plus to minus, plus to minus. Or as they say, it can be written as something that's causing it to flip back and forth multiplied by some u of n. In other words, a sub n is equal to the alternating part times something that provides the number part. So think of u of n as being a series of positive numbers and then multiplying by something that provides the back and forth, back and forth. Okay, if every term u sub n is positive, meaning it's truly an alternating series. If u sub n is greater than u sub n minus 1, meaning that these positive terms decrease. And how could you show that? Well, you make it into a function, and then you look to see if the function, the derivative of the function is less than 0. Kind of like what we did for integration test. And if the limit of u sub n goes to 0, then the series converges. So if it's alternating, decreasing, and the limit goes to 0, it converges. Now let me tell you how you actually end up doing this in real life. You look at the nth term, you strip off the alternating part, you take the limit of it. If it goes to 0, it converges, and if it doesn't, it diverges. Done. I look at this series. Yeah, I can take the time to find out if it's decreasing. I probably won't. I probably will short shrift that. But I say, hey, what's the limit as n goes to infinity? And I wipe out the part that has the alternating part, and I say, hey, what's the limit as n goes to infinity of 1 over n? 0. Therefore, convergent. Done.
Wait, did I already say that 1 over n is?
Oh, no. I did say the series 1 over n is divergent. This is the series negative 1 n plus 1 over n. This particular series is called the alternating harmonic series. And it is a known convergent series. So what makes it so different from the harmonic series? That the harmonic series diverges and this one converges. Well, think about the fact that if you're adding numbers and you're adding a number, but the next number you add is a negative number. You add, you go back down. You add, you go back down. You add, you go back down. It's a lot easier for an alternating series to converge than it is for one that's made up of all positive numbers. The amount of work necessary for getting an alternating series to converge is just really small. Does the nth term go to 0? Done. That's it. I love alternating series because after doing the integral test and the p-test and the geometric series test and the limit comparison test and the direct comparison test, this is a breath of fresh air. Are you ready to go on?
No.
All right. Ready now? It's in the book, too. You good? All right. Now, there's one other part about the alternate series test that makes it also really, really nice. Remember I told you how we totally skipped section 9.3? It had to do with what's called error calculations. Here's the idea. If I take the alternating series, the alternating harmonic series, 1 minus 1/2 plus 1/3. In fact, I have a name if I stop here. I would call that the third partial sum, right?
Yeah.
The third partial sum is an estimator to the real sum. It's approximately equal to S. It's not really equal to S. I only could get S if I go out an infinite number of terms, but the third partial sum is an estimator for how close we are to S. Or sorry, it's an estimator of S. But how close did we get to S? How close are we to the real answer? Well, if I take any nth partial sum and I subtract it by S. Now, maybe S sub n is a little bit too big, maybe S sub n is a little too small. let's make our lives easier. Let's take the absolute value of that. We have a special name for that. S sub n is a guess. S is the real answer. The absolute value of their difference is called the error. It's how far am I from the real answer. Are you ready? How close am I to the real answer? The answer is I am less than the absolute value of a sub n plus 1. If I stop at 3, and I want to know what the error is, my error is less than the absolute value of negative 1/4, the next term. I am within negative 1, I'm within 1/4 of the real answer. And it's called the alternating series error estimate. Now, there are other error estimates that I totally blew off. They're much more complicated. But if we're lucky, this is the one that they'll ask us about on the exam. If we're not lucky, we say, we blew that off. You guess if it's a multiple choice. You guess if it's a free response, too. And you move on. You don't worry about it. Okay? That's just how it played out. Remember all those good times we had? Well, we traded all those good times for 9.3. Fair trade. Remember that Ernie's one day? It was delicious. 9.3. That was the victim. All right? So, let's do another.
Really close, I just said.
Really close. We're about to do another alternating series problem, and at the end of it, I'm going to ask the question, how close is our answer? Right? And you'll give me your response. Are you ready? Let's go. So here's another question. Is this alternating series convergent or divergent? If we're rigorous, we check to see if it's decreasing. We check to make sure it's all positive. But typically what we really just do is, hey, it's alternating, take its limit. The limit, as n approaches infinity, of 4 over 2 to the n. Zero. Therefore, the series converges by the alternating series test. Alternating series test. All right? Hey, you know what? I took this sum, -2 plus 1 minus 1/2 plus 1/4. I added them up. How close is that to the infinite series?
Within 1/8.
It's within 1/8. Less than 1/8 away. You like that? No, I'm just saying, it feels like this stuff was so hard over the last few days. And this feels so nice.
One of the last few chapters.
Wait, I don't understand why is this nicer than what we just did with the L.
Okay, in the limit comparison test, the limit comparison test, we had to look at it. We had to determine what series did it look like. We had to determine whether the series that it looked like, whether that was convergent or divergent. And then we had to take the limit and get a positive finite value to finish it off. This one, I don't have to find another limit. So I don't have to find another series. I have to take one limit, and all I have to do is make sure it's 0. That seems really easy to me compared to what we just did. But it only works on alternating series.
Where did you get the limit? I mean, before.
I got that from looking at the nth term and stripping out the thing that causes the -1 plus 1, -1 plus 1. I ignored that piece of the nth term.
You just take it out.
Yeah, because what we call this, like when they're saying the alternating, we've got the part that does the alternating, and then we've got everything else. That's what we call u sub n. Right? All right. Your turn. Why Divergent, Anthony?
Because when you take the limit of n, as n approaches infinity, you're going to get infinity and not 0.
So it's divergent. By?
Yes.
Nope.
Yes.
Nope.
Nth term.
Remember we had a thing called the nth term test for divergence? We proved convergence with the alternating series test. We proved divergence using the nth term test.
Where was that?
Maybe when you were sleeping.
Oh, it's 9. No. I wrote that one down. I was not sleeping. That was 9.
No, don't go for it.
It was 9-4.
9-4, okay. Yes.
Can you just look at the series and say
It looks
each
like-
term is going away from 0?
That's exactly what's getting summarized by that infinity, but that's the intuition I want you to grab onto. And you say it's getting bigger than 0, therefore it must be? Yep. All right. 907 or 307? Okay. Now, got one more thing to deal with. Okay, you know what? I've got some words written here, but I would rather do it. I'd rather do this way. Are you ready? I'm going to draw a picture. Huh? Huh.
Again.
Okay. We had that right. I want to look at this particular series. 1 minus 1/2 plus 1/3 plus 1, minus 1/4. I want to look at that alternating harmonic series one more time. I want you to tell me where in that Venn diagram do we lie? Or lay. I can't remember which one's which. Okay, if you say so. Your father's a writer, mine's a sheet metal worker. You probably would know better than me. No, I don't want to go there. I want to answer the question. Is this series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, is it in the divergent area?
No.
Okay, great. So it's in the convergent area. Is it in this area or is it in that area? In here? It's in one of them. You have 50% chance of being right.
Yes.
Is it here? Because if it's absolutely convergent, that means when we strip off all the negative signs, we get a convergent series. Is that what happens with that?
It's harmonic.
It's harmonic. We are in here. Okay, now, this area is called the absolutely convergence area. This area here needs a special name. If it's convergent, but not absolutely convergent, it's called conditionally convergent. All right, you've got the ability to do almost all of the homework. I think through problem like 31, you can do through problem 31 right now. We'll finish up with the last portion tomorrow and we'll really be done with chapter 9.
I was awake.
You were awake. Indeed.
I was awake.
And in a good mood. And participatory. And all sorts of really, really great things.